mathematical age.
I've got all these points here, but I wish there was a better way to represent them in two-dimensional space.
Yeah, those aren't very good. They're just in one single dimension.
Well, what would you make? How would you make them better?
Well, my friend, have you ever heard of a vector?
No, never.
Well, my friend, a vector is just like these points. However, it lives in a multi-dimensional plane. Consider R2. The head can be defined as these points, and the tail, the origin. The vector represents a directional force between these 2 points. Now, a vector has 2 very important defining characteristics. One, magnitude. The second, direction. Now, these 2 properties are very essential to a vector and define it fully. Let us first consider magnitude. The general definition for an n-dimensional vector is the square root of the sum of the changes between its components. Now, that is quite a lot of stuff, but if you think about it, since a vector is defined only by its direction and magnitude, what we can do is take any vector, like this little man over here, and since we know his magnitude and vector and direction, we can move him so his tail rests at the origin.
How neat is that?
Pretty neat. Thus, all of the second components fade away and the delta becomes 0, meaning it is just the square root of the combination of all possible vector components. Now, let's take a couple examples in our favorite dimensions, R2, and R3.
And R4.
Not R4. Not R4. We do not like R4. Now, in R2, a vector has both an x component and a y component. Since we can rewrite each component as the tail being represented at the origin, you can simply square the x and the y and take the square root, and that will give us our magnitude. And in 3 dimensions, we carry on the same paradigm. This time we square the x, the y, and the z, and take the square root, and we are done with the magnitude. Now that we have defined magnitude, let's take a little bit of look at the direction of a vector. The direction of a vector is this angle theta with respect to the origin.
Whoa, that's pretty neat.
How neat is that?
Pretty neat.
Pretty neat. Now, since vectors, by definition, are a subset of vector spaces, let us look at perhaps multiplying them by scalars.
So you're saying there's closure under multiplication?
Closure under multiplication. For example, let's say we have this vector, v1, and it is defined by 1, 1. What we can do is multiply this vector by any real number. Give me a real number.
6.
6! Let us multiply this by 6. It extends its length, magnitude, increasing, until thus the same direction is kept, but now the magnitude is 6. Furthermore, in this multiplication by scalars, we have a secret, a trick. This trick is multiplication by negative numbers. What we can do is multiply a vector 1, 1, originally here, by the scalar -1, and magically it flips it, it inverts it by a theta 180 degrees. Whoa. We have kept the length, the magnitude, the same, but in doing so, we have completely reversed the direction. Furthermore, like being closed under multiplication, that is also closed under addition. So, if we have 2 vectors, consider the vectors 1, 1, like we have drawn before, and 2, 3, up here. what we can do, like anything else, is add their components likewise. To get the vector, 2 plus 1 is 3, 3 plus 1 is 4, 3, 4. Boom! Just like that. Now, we conclude with one final thought. Vectors, a way to represent things in n-dimensional space. They have direction, they have magnitude. They are, you can multiply them using dot or cross products, which is a little more complex. You'll learn about that in the future. But now we can add them, multiply them, and figure out their magnitude and direction.
So you might think you lift, but do you even?